Hello students, and welcome to section 7-2, multiplying polynomials. So what we're going to go ahead and do today is take a look at how in section 7.1 all of those features of polynomials could be put into the context of multiplication. So let's take a look. Example 1. Multiply a monomial and a trinomial. What is the product of negative 4x to the third, or negative 4x cubed, which is a monomial, and x squared plus 3x minus 4, which is a trinomial? In multiplying these two together, you are going to have to distribute. So using the distributive property works for polynomials in the same way that it works for real numbers. So let's take a look. If we multiply through, notice we are setting up for distribution. As you can see in red, this monomial distributes to this black polynomial x squared, 3x, and negative 4 as such. So negative 4x to the third times x squared, negative 4x to the third times 3x, and negative 4x to the third times negative 4. So again, distribute to each part. As it turns out, we can see here that we are going to be adding the exponents as we reflect upon prior sections. 3 plus 2, of course, is 5, so we have negative 4x to the fifth. Here we have x cubed plus just x to the first, or times x to the first, which 3 plus 1, of course, is 4. And notice negative 4 times 3 needs to be done as well, so negative 12. And then lastly, negative 4x cubed times negative 4, that should just simply be positive 4, and then x cubed on its own stays there. So we're distributing negative 4x cubed to each term of the trinomial. The product is exactly what we see here. Negative 4x to the fifth minus 12x to the fourth plus 16x to the third. Notice that the product of these two polynomials is a polynomial. Example 2. Use a table to find the product of polynomials. How is multiplying binomials like multiplying two-digit numbers? So what we're going to go ahead and take a look at is multiplying the expressions 15 times 8, but also x plus 5 times x plus 8 in a table. So in this table, as we can all see hopefully here, what we've represented here on the left, what they've represented 15 times 8, which you can write in expanded form as 10 plus 5 times 10 plus 8. So 10, again, plus 8, that's 18, and 10 plus 5, that's 15. 10 times 10 on its own, of course, is 100. 10 times 8 is 80. 10 times 5 is 50, and 8 times 5 is 40. Here, okay, without actual numbers for x, the same type of setup applies. So x plus 8 and x plus 5. X times x, that's just x squared. 8 times x, that's 8x. X times 5 is 5x, and 8 times 5 is 40. So how do these correlate? So if we take a look, the setup for this math accordingly is simply you adding up all of the numbers that you see in the table. So 100, 80, 50, and 40 added up are 270. Here, these four terms can't necessarily be added in the same manner, but in a sense, you're still writing them out as a sum. So x squared plus like terms 13x, and then plus 40. You can multiply both binomials and two-digit numbers in expanded form using the distributive property. I do urge that you test to see what would happen if you were to plug in, let's say, a number here, let's say 10, frankly, but also a number here. Let's try 10 maybe again. If you were to try plugging in 10 for x here and 10 for x there, in other words, 10 plus 5 times 10 plus 8, but also plug it in here, 10 squared plus 13 times 10 plus 40. I urge you to try that, but it should end up being the exact same result. And again, the reason is we're just replacing 15 here with 10 plus 5 there, but also 10 plus 5 here. And the same goes with x plus 8 and 10 plus 8. So the answer should still be 270. What is the area of the green rectangle? Okay, so let's take a look. The area of the green rectangle is represented by the expression as we see 2x plus 1 and x plus 3. Okay, so the nuances of the picture, and yes, we've talked about geometry in the past and how it applies in different ways. This is really just to help us frame our understanding a bit more. So the height of the rectangle is represented by 2x plus 1. So here's 2x, and here's the little extra part, 1. So 2x plus 1 in its entirety is the height. Okay. The width of the rectangle is very much the same, except here is x. And then you have 3 smaller squares to kind of scoot next to that or squeeze next to that. So x plus 1, 2, 3 smaller squares. Okay, now dimensionally speaking, like the algebra tile problems we've done in the past, this length, okay, and that width speak to a singular rectangle in white here with dimensions of 2x by 1. This square is 1 by 1, this rectangle is x by 1, and these small squares are each 1 by 1. In total, of course, because you have 3, you add those 3 squares together. Okay, so how are we going to put this together? The area of the green. We use a table to find the area of the section, or each section for that matter, excuse me, of the rectangle. So we're going to combine like terms simply by doing the same type of process like we saw in part A. We'll take 2x plus 1 and write it in this context, and then x plus 3. 2x times x, that's 2x squared. 1 times x is x. To get 6x, you have 2x times 3. And to get 3, 1 times 3. Let's combine the blue-like terms, as they suggest here, technically speaking, in the next step, which lends itself to the following. 2x squared plus what? 6 plus 1 is 7, so 7x. And then lastly, just 3. Again, the product of these two polynomials is a polynomial. So 2x plus 1 by x plus 3 multiplying is, in a sense, very much like multiplying a length and a width of a rectangle to get the area. Okay, the algebra tiles were a nice way to kind of help us see how we can work with polynomials. This is certainly a very similar approach, kind of yielding, in this case, the product, not the sum, as we saw in a prior section with algebra tiles, but the principles are very similar. Example 3, multiplying binomials. How can you use the distributive property to rewrite 2x plus 4 times x minus 5 in parentheses as a polynomial? Well, distribute each term to in the first binomial to each term in the second. So what we see here is a process of distribution wherein we're taking the red term, multiplying it by x minus 5. So separately you see here 2x times the quantity x minus 5. And then we also see in blue 4, and then as you can see separately times parentheses x minus 5 again. So we're distributing the red and the blue terms to the second binomial. And then if you continue, you can start the process of multiplying again. So you distribute the 2x to the x minus 5. Here's just times x. Here's just times negative 5. And then 4 times x, 4 times negative 5. Multiply, and you have 2x squared minus 10x plus 4x, and this of course is negative 20, or minus 20 in the end, when you look at all the terms together. Your like terms are in fact the green ones, negative 10x plus 4x, and therefore 2x squared minus 6x minus 20 yields your standard form, is what we say. Therefore the product of these two binomials is 2x squared minus 6x minus 20. Again, the product of these two polynomials is a polynomial. So this distributive property approach does work quite nicely in the sense that you can see how each part multiplies through. multiply a trinomial and a binomial. How can you use a table to find the product of x squared plus 2x minus 1 and 3x plus 4? Write the terms for each polynomial in the first row and column of the table. Multiply to find each product. Okay, so this is very much like what we've done already. We can see on the top here we have x squared, 2x, but also negative 1. And on the other side of the table we have 3x and 4. 3x times x squared, that's 3x cubed. 3x times 2x, 6x squared. 3x times negative 1, negative 3x. 4 times x squared, 4x squared. 4 times 2x, 8x. And 4 times negative 1, negative 4. That process, take your time again if you need to go back. Take a look and see how those unfold. But that is the resulting products. So those are the resulting products. Okay. Combine like terms. Okay, it has been color coded again for you, and I think that's very helpful. We have two red terms of 6x squared and 4x squared to add. Those are like terms, so we're going to combine those. And then we have negative 3x and 8x, which are also like terms. We'll combine those in a moment. As it turns out, the other terms are standalone. We can't touch the negative 4, for example, nor the 3x cubed. So you can see here in the next step, 3x cubed plus 10x squared, adding 6 and 4, plus 5x minus 4. So x squared times 3x plus x squared plus 2x minus 1 times 3x plus 4 is equal to this cubic polynomial when you multiply a trinomial and a binomial. The result is 6 individual products. Using a table is one method you can use to help organize these products. Again, this table approach is very nice to see how the terms are multiplied but also combined when it's all said and done. Example 5. Example B of part 4. Okay, example B. So how is multiplying a trinomial by a binomial like multiplying a 3-digit number by a 2-digit number? Let's consider the products 312 times 24 and 3x squared plus x plus 2 times 2x plus 4. So what we can see here, and I hope it's apparent, and it does relate to something we've done in the past, if you multiply each place of the 3-digit number by 4 ones and 2 tens, then find the sum. Okay, so let's follow along here. So the math on the left does speak to a typical multiplication of the 3-digit number times a 2-digit number. So 2 times 4 is 8, 1 times 4 is 4, 3 times 4, of course, 12. You have a place values system here where you have 0 placeholder essentially. 2 times 2 is 4, 2 times 1 is 2, 2 times 3 is 6. Add these up, and these are your like terms. So this is the part of the problem where it will nicely relate to that, at least in the sense that they're lined up. And the multiplication, of course, also is very much like what we'll see here in a moment. The answer is not identical to this because, well, we're working with numbers specifically. But here's where they are drawing connections. So notice the blue and the red terms kind of correspond to these two blue and red terms. Multiplying 2 times 4, 8. 4 times x, 4x. 4 times 3x squared, 12x squared. Similar to this, we have the same type of placeholder, so to speak, here. 2x times 2, 4x. 2x times 1, 2x squared. 2x times 3x squared, 6x cubed. Terms are vertically aligned, and you can add these as like terms. 8 plus 0, 4x plus 4x, 12x squared plus 2x squared, and 0 plus 6x cubed. So these two answers, although not identical, obviously, it's a nice way to see that we are in fact adding like terms in a very similar type of manner. And of course, aligning them in such a way where we can easily represent them. When multiplying a trinomial by a binomial, you multiply each term of the trinomial by each term of the binomial. This is similar to how when multiplying a 3-digit number by a 2-digit number, you multiply by each place value of the 2-digit number. Please continue the last examples on your own.